here we are at day 3. We've been practicing for our design presentation, which is coming up in a half hour. We've been running through it a bunch of times, so it's looking pretty good. Making a few last-minute changes for lane detection, the autonomous challenge. Been doing some tuning for stuff for the navigation challenge. So we still have, after the final presentation today, we'll have tomorrow to keep working on that stuff, and I think it'll be pretty good for Monday.
So it's sunny outside right now, but this morning when we came out, it was raining really hard. So when we got here, I decided to put some tape over the seams in the robot, so if it rains again, there will be less water going in.
My name is Gordon Franklin. I'm from Princeton University, and I'm here with two of my teammates, Chris Molisano and Jonathan Mayer. This afternoon, we're going to tell you about our robot, which we call the Kratos. When designing Kratos, we followed the general robotics paradigm known as sense, plan, act, in which you sense the environment around the vehicle, plan a set of actions through that environment, and then act on those actions. However, we also identified a fourth element in this loop, which we call substrate. And substrate is basically the way that the data flows between sense, plan, and act. And so we're going to discuss each of these four elements in detail with respect to the implementation of Kratos.
So the problem we're trying to solve during the sense step is what is the best possible representation of the environment for the vehicle. We solve this problem in 3 steps. First, we use sensors to perceive the state of our surroundings. Then we use algorithms to extract data from these sensors. And finally, we fuse the data from the sensors into one coherent possible. One innovation our team made was that we only use one environmental sensor on the vehicle. Both our lane detection and our obstacle detection is all done using one color stereo camera. We also have these 3 state sensors that help us determine the pose of the vehicle. As you can see, all of these sensors, the compasses in here, all of these sensors are located above the pivot point of our vehicle. So we only have one reference point for all of our operations. The last filter was a creative one that we came up with, which takes advantage of the fact that we're doing obstacle detection and lane detection on the same camera. So what we do is take the obstacle points we detected from the obstacle detection step and make sure that we don't detect lanes on these points. This stops us from detecting lanes on light objects. As you can see here, this is running, we're live on the robot. At this time around 100 seconds, we suffered an outage of GPS for about 10 seconds. And the heading for our robot was still able to recover fine just by falling back on the compass and wheel adaptation.
So the planning problem, as we see it, is how to formulate a desired set of actions that best achieves the mission objective, whether that be a pre-specified waypoint in the navigation challenge, or just staying in your lane in the autonomous challenge. And our approach was twofold. First, we wanted to make sure that we reduced the planning problem to a well-understood problem that we could efficiently solve. And secondly, we wanted to make sure we utilize all available environmental data so we plan what would be, as best as we could tell, an optimal path. Our ASR algorithm uses 2 heuristics instead of the traditional 1. We first use a Manhattan distance heuristic, which ensures that we expand as few nodes as are required to find an optimal path. But we secondly use a tie-breaking heuristic between paths to ensure that we pick the straightest path possible. What this means is, as you'll see in a moment when we come around this bend, we'll take paths that direct us directly towards the waypoint. Otherwise, with the Manhattan distance heuristic, you can take points that have cell-wise the same distance, but are not actually straight, and when collapsed into Euclidean distance, don't actually go as straight as possible. And I'm going to show this so you can see a straight path here.
For starters, we have a path tracker module, which uses what is essentially a pursuit point algorithm, where we compare the angle of the robot with the angle of the path, and set our desired geometry as proportional to that angle. In addition, we then set our desired forward velocity. And then using a model of the vehicular dynamics, we're able to derive individual speeds for the left and right wheel.
So how do you reliably share information between your hardware and software modules in the sense, plan, and act cycle? And our approach largely rested on message sharing. We used Carnegie Mellon's IPC robotics framework, which provides a messaging abstraction between all of our services or code modules, which are implemented as individual processes. We thought we could do a little better than Carnegie Mellon's C-based IPC using C++. So we wrote our own C++ wrapper for IPC, which we've lovingly dubbed IPC++. I want to walk you through how IPC++ works here. This concludes the formal part of our presentation. We're happy to take any questions you have, and we're extremely proud to present Kratos.